Paul. Okay. Good.
Okay. Oh, okay. Let's start. So today, we're very happy to have Zhou from Tianjin University. He will talk about the modular space of parabolic bundles over a curve.
Thanks for the introduction of Professor Fu, and also thanks very much for invitation from the committee of AGEA, and for the invitation from Professor Weiping Li. Okay, today my title of my talk, the title of my talk is modular space of parabolic bundle over a curve, and we mainly introduce an argument, a degeneration argument to prove the Verlander formula for the global, for the dimension of the global section of theta function over the modular space, and then explain how the degeneration argument can help us to prove F-splitting of the modular space over a generic curve in partitive characteristic. Okay, this page is an outline of my talk. The first three parts we work over complex field, and the last two parts we work over an algebraic closed field K or partitive characteristic. Okay. Then we begin with some background about comfort blockers. Let C be a smooth projective curve over the complex field, and UC omega be the modular space of semi-stable parabolic bundles on C. Then canonically there exists an ample bundle theta over the modular space U, and the element of the global section of the theta bundle are called generalized theta functions. If we fix the determinant of the modular space, then the space of global section is related to the space VC of comfort blocks, which are the basic object of rational comfort fields theory. In fact, the dimension of the global section of theta over modular space U and over the modular space UL with fixed determinant has the following relation. So it is fine to just consider the modular space UC omega without a fixed determinant, because for some technical reason, it is not easy to generate the determinant map to a singular curve, because there is no natural way to define the determinant bundle for only torsion-free shift over a singular curve. Okay, then the rational comfort field theory tells us the following factory rules for the dimension of the number for the dimension of the global section of theta bundle. The first one tells us we can reduce the genus by 1, but with increase the parabolic poise 2. And the second one tells us we can reduce the parabolic poise. Yes. Then these two formula inspire a degeneration argument about the modular space to prove the Verlander formula for the global section H0 as the dimension of the global section of theta bundle. This approach was proved by non-sigma lambda for lambda 2 case and by Professor Sun for arbitrary ranks. Is called a finite dimension proof of Verlander formula, which is named by Beauvais in a reference. Yeah, okay. So we draw a picture, tell us the presence of the degeneration of curves. The first one degenerate a smooth curve to an irreducible nodal curve with only one node And this corresponding to the first formula in the above lemma. The second one degenerate a smooth curve to a nodal curve with two smooth connected components. It is corresponding to the second formula in the lemma. In this talk, we only detail in the first case, means the degeneration argument for irreducible case. Yes. Then when we consider the family CS over S, then relatively there is a family of a flat projective family of the moduli space UCS omega. And relatively, the theta bundle can also defined in this family. Then we can prove the first cohomology of the theta bundle over the closed fiber vanish for any closed point S in S. This needs some time to prove, and we do not go into its detail. We just use it. So if we have this vanishes, so it is easy to see that the global section of the theta, the dimension of the global section of the theta bundle is invariant for any S. So we reduce the computation of the dimension of the global section of generalized theta function to the modular space on a singular fiber, which just is X, the singular fiber X, an irreducible nodal curve. Yes. Then in this case, because the underlying curve is not smooth, so we can take its normalization. We just denote it by pi. Pi is the x tilde is the normalization of X. Then corresponding the modular space is on U X omega is only semi-normal, and it also has a normalization. We denote it by P omega, which is the modular space of generalized parabolic sheaves over the smooth curves X tilde. Then later, we will prove the factory theory by consider this normalization. Then at the moment, now we give a more detail about the normalization phi and the modular space P omega. Okay. Okay. First, we can fix a parabolic bundle E in the modular space of parabolic sheaves on X. We note that not every parabolic sheaves in UX omega is a bundle, because X is a nodal curve. So the parabolic sheaves, the underlying sheaves, only torsion-free, not maybe not locally free. Okay, we just fix locally free one. Then it's pull back pi star E enjoys the following property, because E is a bundle. So pi star E is fiber over X1 and X2 is are isomorphic, and they are both isomorphic to the fiber of E over the closed point, the nodal point X0. Then we can consider its graph. Then the graph is Q dimension quotient. Then we obey a pair pi star E and the quotient. This is an element of the P omega. Then because we need to get a proper modular space, so we need to consider all the quotients, not just only the graph. It's graph, because the graph is particular. The morphic from the first factor and from the second factor to the quotient are all isomorphic. It's very special. Then we also explain how we can obey the morphic phi. Then giving a pair pi star E Q in the P omega, then there is a exact sequence as following, where X0 pi star E X2 is the skyscraper shape of at the point X0, and the morphic is induced by the quotient Q, and let F be the kernel. So from the pair pi star EQ will obey morphe F over X. So this presence defines the morphe pi, and we can see pi is an isomorphism and only the open subset that the quotient Q just comes from the above graph. So moreover, pi is a normal, and this morphe phi is not isomorphic, but it is finite. It is the normalization or the semi-normal variety or the UX omega. Yes. So yeah. Okay. Then we make a quick review about some basic definition of parabolic sheaves on X, and it's the condition of semi-stability and their moduli space. Okay, let X be a projective irreducible code with at the most
Zhou Minshou. So I cannot hear you. Yeah. Can you hear me? Zhou Minshou, maybe your net is very slow. Okay, Zhou Minshou.
Okay.
Okay,
So,
maybe you can continue. Yeah.
Okay, I'm sorry. Okay. Then in order to make the modular space, we must fix some date which means the flag type, which just fixes the dimension of the quotients Q, I, E, X, and some parabolic widths. Then, similar as the ordinary sheaf case, we also should consider the subsheaf E plus or E, and there is a natural induced parabolic structure on E plus, whose quotient QIE plus X is just defined its image from E plus to E, then to QIE X. Okay, then similar as the ordinary curve case, we can define the parabolic degree of the parabolic sheaf E and its subsheaf E plus with the induced parabolic structure. Then E is called semi-stable or stable, which means for any non-trivial subsheaf E plus, we have the parabolic slope is smaller than the parabolic degree of the E, then stable corresponding to strictly small. Yeah. Under this condition, the GID theory tells us there is a moduli space or semi-stable parabolic sheaf, and there is also an open subset UXS, which consists of stable parabolic sheaf. And because in general, X is just a nodal irreducible curve, so in general, the moduli space is just semi-normal. But when X is smooth, then the variety UX is normal with rational singularity, and its open subset UXS corresponding to stable parabolic bundles is smooth. And to simplify notation, we denote by omega by the the parabolic date, and the moduli space simply by UX omega or UX. We also make a quick review of the definition of generalized parabolic sheaves. Okay. Then when X is a projective irreducible curve with one node, then we can consider its normalization pi from X tilde to X. Then the preimage of the node point X0, we denote it by X1 and X2. Okay, then a generalized parabolic structure of E at the divisor X1 plus X2 is a r-dimension quotient Q from the vector space EX1 divided sign EX2. Then the pair EQ is said to be a generalized parabolic sheaf. Then similar as the parabolic sheaf, we can also consider the parabolic structure outside X1 and X2. Okay. Then similar as before, by GIT theory, we must consider the semi-stable and stable elements of generalized parabolic sheaf, which is defined similar as before. Yeah. Then the generalized GID theory tells us there exists a normal moduli space P omega or semi-stable GPS on X tilde. This is just because X tilde is the normalization of X. The underlying sheaf, the underlying curve is smooth. Moreover, its open locus corresponding to stable GPS on X tilde is an open subset, and it, yeah. Okay, then we can go to prove the factorization or generalized theta function inspired by the rational comfort blockers series. Okay, then recall that we know there is a normalization, the moduli space UX omega is semi-normal because X is just a nodal irreducible curve. So it is naturally to consider its normalization. Then we find that its normalization is just a P omega, which is just the moduli space or generalized parabolic sheaves over the curves X tilde. Yeah. Then we will go to prove the factory or generalize the theta function by consider this normalization. To explain the proof more clearly, we make some assumption. We just assume that the moduli space Ux tilde omega is fine, which means has a universal family, and the projective the moduli space P omega just the Grassmann bundle of Q dimension quotient of the fx1 direction fx2. This is the Grassmann bundle over the modular space Ux tilde omega. Then, under above assumption, the modular space P omega has a canonical divisor D2, which is defined by fx2. The morphism from fx2 to the quotient Q is not an isomorphism, where this morphism is induced from the universal quotient fx1 direction fx2 to the Q to Q. This is the universal quotient over the Grassmann bundle. Then, by studying the normalization phi, there is an isomorphism of the following vector space, which is just says we can reduce the computation of the dimension of the theta bundle over the modular space Ux omega to just compute the dimension theta minus D2 over the modular space P omega. Okay, so thus our problem reduce to give a factorization of the bundle theta minus D2 over P omega in terms of space or generalized theta function or modular space over X tilde. Note that by our assumption, the modular space P omega is just a Grassmann bundle over the modular space Ux tilde omega. So because we only consider about the global section, so we can first take a direct image of the theta minus D2 over Ux tilde omega, then take the global section. This is the same. So fiber-wise consider the morphism P omega to Ux tilde omega. We obey a family of Grassmann variety, just the R dimension quotient of the vector space E1 direction E2, where EI is the fiber of the vector bundle Fxi over a closed point of Ux tilde omega. Then we can restricting the line bundle theta minus D2 over this Grassmann variety. Then by some computation, it is just the line bundle L2 k minus 1 power, where L2 is the tensor determinant E2 and the determinant of Q. So fiber-wise, we get a family of section or a line bundle over the Grassmann variety. But we know over the Grassmann variety, there is a natural GLE1 tensor GLE2 action. So this section is a representation of GLE1 tensor GLE2 of weight k weight equal to k minus 1. So by a general theory or representation over the complex field, because in this part we work over the complex field, there is a decomposition of the representation, where S mu is the Zhou functor determined by the sequence mu. Note that this is the vector space S mu E1 just equal to the global section of some line bundle L mu on the flag of E1, where L mu and the flag type N mu is determined by mu, and we do not go into the detail. So globally, it is equivalent to say we add two more parabolic structure at the point x1 and at the parabolic point x2, because E1 and E2 is the restriction of F at the fiber x1 and x2. So So by push forward theta minus d2 through the normalization, the above lemma implies the factor theory or generalized theta function as following. This was proved by non-sigma lambda for rank 2 case and by Professor Sun for arbitrary ranks. Okay, and we have the following isomorphism. Okay, we continue. Then we have the following factories, which the genus on the left hand is G, the left hand. So we can reduce the computation of the dimension of the theta function to the modular space or a curve, but with genus reduced by 1. And so we can reduce our problem to just compute the dimension of generalized theta function over P1, but with many parabolic points. And by degeneration to reducible curves, we can also reduce the number of parabolic points. Finally, we just only consider the case P1 with 3 points, which can be done, or which can be computed by a detailed computation. In summary, we use the argument, we use the degeneration argument to give the Variant formula for the dimension of the space or the global section or the theta bundle or the modular space. Okay, our proof is based on a purely algebra geometry argument, so it is called a finite dimension proofs. Okay. Then we go to the second part of my talk. In this part, we will go to explain how the degeneration argument can help us to prove the F-splitting or modular space over a generic curve in partitive characteristic. Okay. The concept of F-splitting was first introduced by Mehta and Ramanathan in 1985. Then they first used F-splitting to prove that the subgroup variety in positive characteristic are all reduced. This is a bigger breakthrough. Then its definition is as following. For simplicity, we only consider an algebra closed field K or positive characteristic, and let V be an algebra variety over K, and F be its absolute Frobenius morphism, which means it is the identity map on the topological space, and the structure map was induced by P power on the local section. Okay, so we get a morphism. Then the variety V is called F-splitting if there is a left section of the structure map OV to F star OV, which it is equivalent to say the following sequence splits. Then it is easy to see F-splitting variety have many nice properties. One of them is the following lemma, which names the high cohomology for any amplified bundle over a proper F-splitting variety vanishing. This will be also a key point in our proof later. Okay. Okay. Then we stated two useful factors about the F-splitting. For the first one, for example, if V is smooth, then by relative duality, the movie, the home from L star OV to OV, this vector space equal to the global section of P minus 1 of the anticanonical bundle of V. So if we giving a section of the anticanonical bundle, we denote it by sigma, then it's P minus 1 power. We defined a map from F star OV to OV. And then if this map splits the structure morphe, which means give a left section of the structure morphe, we call that V is splitting by a P minus 1 power, and the sigma is called a splitting section. Okay, then the second useful factor is the following, means local critically for L splitting. Okay, which let V be a proper smooth variety with dimension n, and x1, x2, xn be a system, a local coordinate at a closed point x in V. Then when the section sigma P minus 1 power splits V, just if and only if the local expansion of sigma P minus 1 power have coefficient 1 for the monomial x1, x2, xn P minus 1 power. So it is very useful greatly, and we will use it in the later proof. And one can easily check if one closed point has this property, then every point has this property. This is just come from the fact because we let V be a proper variety, so its global section are all constant. Okay, we do not go into detail. Easy to see, yeah. Okay, because we will use the degeneration argument, so we must consider a family of modular space. But in general, F splitting is not an open condition in a family of variety, but it is in some special case as following. If we have a family, we have a flat family Vs to S with S smooth, and each generic fiber is normal with the global function are constant. Then suppose give a section of the relative anticanonical bundle omega minus anticanonical bundle. Then if this section splits a non-empty open subset of a fiber, then it splits the fiber in a neighborhood. Its blue is based on the local critically for L splitting, and came from the assumption because we assume the generic fiber has with global section are constant. So and in practice, we always hope that the anticanonical bundle is ample. Then if so, if the anticanonical ample and the special fiber is also a L splitting variety by a P minus 1 power, then this section can split because the high cohomology for any ample line bundle over Vs is vanished. So we can split this section sigma, and by the lemma, this section splits the generic fiber. Okay, we will use this measured later. Okay, so it is important to consider to check whether the anticanonical bundle is ample for general. Okay, we have the following observation. Okay, we later. We first introduce our main result. We will use the degenerate argument to prove the following result, which means if P is large enough, P is larger than 3R minus 2, then the modular space is L split for generic choice of the smooth curve C and the generic choice of parabolic points. And the case The longer 2 case has proved by Mehta and Ramada in 1996. And in here, our argument is divided into 3 steps, similar as the proof for the Verlinder formula. Firstly, we degenerate a smooth curve to a irreducible nodal curve. Then the L-spin of the moduli space is reduced to consider the case over rational curves, but with many parabolic points. Because when we decrease genus 1, then we must add a parabolic 2. Okay. Secondly, we can reduce the number of parabolic points by degenerate a smooth curve to a nodal reducible curve with 2 smooth connected components. Finally, we only our parabola reduced to the case P1, but with 4 parabolic points. In this case, we can study its a special figure geometry. Lowly speaking, in this case, the moduli space is bilateral to a blow-up of the flat variety or a R-dimension vector space along some smooth centers. Then the bilateral is also an isomorphism on an open subset of dimension 2. So we can extend the L3 into the home vector space. And in this talk, we only detail the first part, which means degeneration argument for L-splitting. Okay. From the above lemma, we know whether the anticanonical ample is whether the anticanonical bundle is ample is very important, because when it is ample, then the vanish of the higher cohomology can make us to stabilize the section. Then the anticanonical bundle of modular space in general is not ample, but it is if we fix some special parabolic weights as this lemma. Okay, we don't need the detail. We just tell us the omega is choose to let the anticanonical bundle is ample. Yeah, it's enough. So to simplify notation, from now on, we always assume that the parabolic with omega cent is above requirement. Okay, then similar as before, we have 2 degeneration process, and we only detail the first sense, which degenerating a smooth curve to the nodal 1. Then we give a normalization x tilde to x. Okay. Then relatively, there also exists a flat projective family UCS omega 2s. This is a flat projective family. But because there is a closed fiber is singular, so this modular space UCS is not smooth. And there is a smooth locus, which means BCS omega, which corresponding to semi-stable parabolic bundles. Because the underlying code is not smooth, so semi-stable parabolic shoe may be only torsion free. It may not be locally free. Okay. But because the singular fiber only over X0, so outside the S0, these 2 family coincidence is equal. So okay. Then we consider the normalization. Then we just see the singular fiber over S0. Then in this case, the modular space UX omega is not smooth. But by using the lemma before, the first idea is to prove L-splitting for UX omega, the modular space over the singular fiber. But UX omega is only semi-normal, so it cannot directly prove for some technical reason. Then instead, there exists an open subset BX omega, and over this open subset phi is just an isomorphism. Okay, Then if we can prove P omega is L splitting, then because Bx omega can from this commutative diagonal, Bx omega can also be seen as an open subset of P omega. So if any split section of P omega also can split Bx omega. Okay, then by some technical argument, the split section of P omega can descend to a section of theta over Ux omega and spread over a neighborhood. But we have the following equality, which means the anticanonical bundle of BCS is equal to the restriction of theta over the BCS. So we can just consider this family, BCS over S, because the only fiber is not proper is over S0. So geometric fiber, it is proper, smooth with global section are constant. Okay, so all our problem reduced to prove one is the modular space P omega is L splitting. Okay, then our problem reduced to prove if the modular space Ux tilde omega is split is L splitting, then so is P omega. Okay, where Ux tilde is the modular space of parabolic bundle over X tilde, but with two more parabolic points with full flag structure. Okay, for simplicity, we also assume that the modular space, because we have two more parabolic structure at X1 and X2. So logically speaking, this modular space is the fiber product of the full flag over Ux tilde omega. And the modular space of GPS is just the Grassmann bundle over the Ux omega. So our problem can be proved by the following more general result. We prove a more general fact, which is stated here. We prove that let E1, E2 be vector bundles around 2 on a smooth variety N. If the fiber product of the flag is splitting by a P-1 part, then so is the Grassmann bundle over N when P is bigger enough, just bigger than 3R-1. Okay, so finally, we go to a steps. We go to give a sketch of the proof. Okay, to simplify notation, we denote by X be the fiber of flag variety, and GR denoted by GR, the Grassmann bundle. Okay, then the most important is that we find the following sequence from X to G, the following sequence of morphisms from X to GR. Okay, well, in particular, if R is equal to 2, which means rank 2 cases, they are just one morphism X to GR. This is just the P1, tensor P1 to the 2-dimension quotient of 2-dimension as a Grassmann for 2. So they are just a closed embedding of condimension 2. But in general, there is a sequence of morphisms, then where all the phi I are all bilateral. One part behave well under the bilateral morphism. So we only to prove that sorry. So we only need to prove we can lift the F splitting from XR minus we can lift the F splitting of GR R minus 1 to GR. Similar for the last case. As an example, we just consider the case GR R minus 1 below 2 GR. And this is a condemnation 2 closed subset. Moreover, we found that there exists 2 effective divisor D1 and D2 of GR. Then the effective divisor with canonical section S1, S2. Moreover, they sentenced the following property. The intersection D1 and D2 is just equal to GR R minus 1 and omega minus 1 minus D1 minus D2 restriction to GR R minus 1 is just equal to the anticanonical bundle of GR R minus 1. So from this equality isomorphism, we have the restriction global section of GR R minus 1. Then we can prove it is a surjective map. We remark here this surjective map can be proved by show some representation in positive character is completely reducible. This is true over complex field, but it is not true in positive character in general. But it is true if we can choose the P is big enough. So this is why we should assume that P is bigger than 3R minus 2. Okay, from this surjective map, we can lift the sigma, a splitting section of GR R minus 1, and for the lifting is denoted by omega sigma tilde. Then pi tends the canonical section S1, S2, so we obey a section of the anticanonical bundle of GR. So we only have to prove the P minus 1 power of S1, S2 sigma tilde splitting GR. This can be proved by the local correctly. Then we show here. Let n be the dimension of GR. So because GR is smooth, so and we can choose the local system x1, x2, x3, xn at some point x in GR R minus 1. Moreover, we can assume that D1 is the zero section of x1, D2 is the zero section of x2 locally. So the coordinate x3, x4, xn is just the local system of x in GR R minus 1. So the local quality of F splitting implies that x3, x4, xn p minus 1 occurs with coefficient 1 in the local expression of sigma p minus 1 over GR R minus 1. So by multiplication with S1, S2, just locally is equal to by multiplication with X1, X2. So this is clearly that X1, X2, X3, Xn p minus 1 has the coefficient 1 in the local expression of S1, S2 sigma tilde p minus 1 part. So from the local correctly, we are done. Okay, my talk is over. Thank you very much.
Thank you. So are there any questions or comments?
I'm sorry, the Wi-Fi is not work well.
Okay, maybe you can explain in the digitalization process, you reduced everything to 4 points on P1.
Yes.
And then this model space you say it's variation to some blow up or something.
Oh, the flag variety or a vector space, R dimension vector space.
Which variety? Flank variety?
What?
Is
Flag
it blow up?
blow up some smooth centers.
Of some flank variety. Which flank variety?
Oh, flag. We mean E is the R dimension space. Then consider its flag OE or full flag type.
Oh, okay.
Yes.
But this should depend on the parabolic data.
Yes. You in general, there is a rational map from this case to the rest one. Then we can do it detail. Yeah. The most case is the full flag case.
So in the first part on the Vernon formula,
yes.
So you also reduce to the case of P1 with 3 points.
Yes, that's with three points. But to prove the F splitting, we must consider 4 points. That's because for some technical reason, it is.
Okay, so the moduli of this with 3 points, what's the moduli space?
We don't know how this moduli space, what the moduli space is. The computation is not easy. We spend some time to prove it. But if the number of parabolic points is 2, then the moduli space is empty or 1 point. But the 3-point case is not easy to see.
Okay, so in your first part, so you put the Vernon formula for GL and for SL, SL or GL?
SL.
Oh. So for other type.
Because there's a relation, relation between fixed determinant and without fixed determinant. Just the last equality here. Okay,
for other Lie groups, you don't know SO, SP, and so on.
There is also a Verlander formula for the other simple Lie algebra, but in algebra geometry, I think there's no way to degenerate a G bundle, a parabolic G bundle to a singular curve. I don't know how to do it. Yeah. I think it is very difficult because the vector bundle we can study it, but yeah.
Okay. So are there any other questions? So if no more questions, so let's thank Zhou Minshou again for his talk.
Okay, thank you, Professor Zhou. Thank you.
Okay, thank you. So maybe so we have